Fabulous. Okay. So this is what it looks like for the retest request form for Unit 1. If you are interested in an opportunity to retake the test because you just feel like you failed it, thank you for your interest in this examination, retaking this examination. We want you to do some self-reflection on what you did to prepare yourself for this past exam, as well as what you could do differently in the future. If you complete the requirements of this request form, I will review and consider the retake opportunity. It's not a done deal. It depends on how you answer the questions in this form. So let's go ahead and see what you need to do. What is your last name? That's easy. What is your first name? What class period are you in? Woo! So far, so good. How did you prepare, or how prepared did you feel for this exam? So this is you on a scale of 1 to 5. I felt really prepared, or I did not feel very prepared at all. And then I'm going to ask you some questions that I want you to be honest with your reflection. Did you write down the daily question, meaning the capture question, every day in class? Not very often. I did this daily. What did you do to prepare for this exam? And then you have to go through each one of these. I took daily notes. I always wrote down what my teacher was writing on the board. A 1, almost never. A 5, daily, very often. And then go through all of these and be as honest as possible, okay? Be honest. If you say, yeah, I did that, yeah, I did that, yeah, I did that, and you're still like getting a 10 out of 25 on my exam, then there's something else we need to go ahead and look at. So be as honest as you can with this. Landon.
Yeah.
You with me?
Yeah.
All right. Which lessons did you find most confusing? Matter notes. Did you understand them completely? Or I was absent and I just didn't make up the work, Mrs. McGrain. So be honest, okay, in here. And then let me move my face out of the way. What is something different that you're going to do for the next exam? Be specific. If you say, I'm going to study more, that doesn't count. How are you going to study more? Be specific in what it is that you are doing. Okay, that's what I want to know. Studying more means what? It means, hey, I'm going to study 5 minutes. I'm going to look at my science material each night before bed, or right after school, or right after dinner. Be specific with your goals so that you can hold yourself accountable, and I can also check to see how you're doing on those goals. But study more is just too vague. Then you're going to be taking a picture of your notes on Redshift and add it here. Then take a picture of your notes on cosmic microwave background radiation and add them here. Submit it. I will look at it. And then I will send you a code so that you can use that code to go in and take another test. It will not be exactly the same test. It'll look exactly the same. But if you have just been someone that has written down A, B as the answers to the first one, you're going to be disappointed if you put in all those answers to the second one. Okay? Things will have changed. Does anybody have any questions? Now, if you are somebody that got a 95 on the exam, am I speaking to you in the class right now? No. Please be happy with your 95 on the exam. Okay? If you really want to try to get as many points as possible, fine, you can do that, but that means I am going through and I'm grading all of those exams again. So I am talking to the people that are like, hey, I got a 10 out of 25. Hey, I got a 12. I got a 15. Okay? Please then have an opportunity at a retake. But if you got a 97% on this exam, this is not for you. Now, I can't stop you from taking it as many times as you want. Well, just one other time. But that means I have to grade them all. Now, if you do worse, the second time, what kind of a teacher am I? Am I going to make you take that worst grade, or am I going to take the better of the two? The better of the two. That's the kind of teacher I am. I am not going to just go ahead and say, sorry, you had another opportunity. You got worse the second time. Now you got an 8 out of 25. I am not going to do that to you. Any questions at all? When is this due? Yeah. Please make sure that this form has been completed by the 26th, because we can't just keep going and going and going. That's fair, right? So that I can kind of process and move on. All right, my little ones, here is your notes, or rather our daily question. It says, what element is a metal and has less protons than selenium, but more protons than zinc? What element, yep, go ahead. We're going to go with Adam on this one. Gallium. Caitlin, do you agree or disagree? She agrees. Can I have one more other person corroborate? Liz also says yes. So gallium, I'm going to spell this and you let me know, Adam, if I'm correct. I have Gallium. And is the chemical code Ga? Great. What is the atomic number on that? All right, atomic number equals 31. That means 31 protons. Jacob, you need to be writing this down or typing it in. Fabulous. All right, so then how about you do the next one then? What elements do you think Jacob could fuse together to make this element? If you can't find it, would you like to pass to your neighbor next door? He's on the clock. Oh, he's got it. So what two other things could potentially be added together to make 31? It doesn't have to be just two things. You want to pass it to somebody else? He doesn't. So we're gonna. Okay, so copper, which is Cu, has how many protons, bud? Okay, so we have 29 protons. And helium has 2 protons. This gives us a total of 31, which is, oops, I'm sorry, that should be the chemical symbol, Ga, which is 31 protons. Good job, Jacob. There you go, there's an example. Now, do you feel like this is something you could do on the exam? Are you going to have your periodic table with you? If you bring it, right, if you have your materials, then you're going to be just fine on the exam. Please make sure you're using your materials. I had one of my students on the last exam for one of the answers say IDK. Like, how could you say IDK? You have all of your materials in front of you, unless they do not have their materials in front of them. So please make sure that you are using your materials. Questions before we move on? Please close your notebook so that you can save the battery. And then we're going to take some notes on stars. You should have this note sheet in front of you. And I printed it in color for you because I really want to make sure that you see the full visible light spectrum. It is 3-hole punched so that I expect you to put it in an area where you will be able to find it once again. If you are one of my students that does not have a folder, I really want to make sure that you have a folder so that you can put all of your materials in it. Let me know and I will go ahead and provide something for you. All right, we're going to have an essential question for both sides of this note sheet. The very first side, which says notes on stars, essential question, is going to be this. This is going to be our focus for this side. Why do people, and actually Neil deGrasse Tyson said this, why do people say, and I'm going to go ahead now and put quotations, why do they say that we meaning humans, are made up of star stuff? End quotations, question mark. Why do people say we humans are made up of star stuff? So by the end of this front sheet, that is going to be what you are going to summarize at the bottom, and you're going to do that after this class sometime today or tonight. So stars, what are they? Well, they're really huge. They are huge spheres of glowing plasma. Plasma is a state of matter. It is the fourth state of matter. You're familiar with solids, liquids, and gas. This is plasma. Plasma is when you get gas super heated and the electrons strip off of the nucleus. And so you've got this soupy thing of nucleus and electrons, and it's just, it's chaos, but it's plasma. Stars make their own heat and light. Here's something I'm going to put on the exam. I'm going to ask you if a star is on fire, and you are going to say no. Stars are not on fire. I'm going to make that all caps. I'm going to underline it. Because every year I have students that say, yeah, it's a burning fire mass of something. It's like, no, it's not. It's not on fire. It's just glowing plasma. Let's go ahead and talk about the closest star that we have to us. Closest, question mark. Can someone raise your hand, please, and tell me, what is the closest star? Adam, you've already participated. Liz, I think you have not participated today. Go, Liz, go. Yeah, I'm going to put our sun. Our sun is the closest star that we have. Our sun is 8 light minutes away from us. The second closest star is what? Somebody ever heard? I mean, like, if you look up in the sky and you see all those stars, which one do you think is closest to us outside of our sun? Okay, it's Proxima Centauri. I did not expect you to know that. How would you know that? Proxima Centauri. Proxima Centauri is 4.2 light years away. Proxima Centauri is 4.2 light years away. Now you might think, oh, that's so close. Let's get into a rocket ship, boys and girls. In 4 years, we'll be at Proxima Centauri. Let's visit the planets that are there. It doesn't work that way because a light year is a distance. Don't write this down. I'm just writing this down for the people at home. So light year is not a time. Light year is a distance. Okay, so let's go ahead and try to think about this. If a light year is a distance, this is the distance that light will travel in 4.2 years. How fast does light travel per second? Do we remember? It is 300,000 kilometers in 1 second. So if we want to try to figure out how far, not how fast, but how far we would go in 4.2 years, we would have to figure out how many seconds are in 4.2 years. Then you would take that number and you would multiply it by 300,000, and that would be the distance in kilometers we would have to travel in order to get to the next closest star, the next closest solar system. That's a long distance. we would not be alive. Our children would not be alive. Our children's children would not be alive. We do not have the technology right now to be able to travel there. You know, we can't even make like a Wall-E situation with like a cruise ship and all these people, right? If we could figure out technology that would be able to travel the speed of light, it would take us about 4 years to get there. Now, space is big. Imagine all the empty space in space, that we are so far distant from our next closest star that we see up in the sky. That's like mind-blowing. Thank you for letting me talk about that, because I think it's fascinating. Let's talk about the energy that we have in stars. How do stars make energy? How do stars make energy? There you go. They generate energy through nuclear fusion. Nuclear fusion. Now, in science, there's a reason for everything. So there must be a reason why they call it nuclear, and there must be a reason why they say fusion, because this is what's happening in nuclear fusion. In nuclear fusion, two nucleus of atoms are fused. What does fused mean? Yeah, combined together to form new. They're not the same. New, more massive, meaning that we've increased the mass, elements. Caitlin. That's a really good question. It's something called parallax. And then what they do, I don't know all the physics behind it. I am so sorry. I don't have that kind of information. All right, so they generate energy through nuclear, but I definitely recommend look that up. They generate energy through nuclear fusion. What is that? That means two different nucleus are going to fuse or come together to form new elements. Let's draw a picture of that, shall we? I'm going to put a little bit of space underneath this last sentence, because I'm going to write something there. And then I'm going to have my good old circle for hydrogen, a little space, another circle for hydrogen. Above that first hydrogen atom, I'm going to say that it has one proton. Above the second hydrogen atom, I'm not going to write the word proton again. I'm going to say 1p for proton. I'm going to put some arrows showing that these two things are going to be coming together, and I'm going to put the word fuse. Fuse means to combine. When this happens, it equals a brand new element. In this case, it will be a helium. I'm going to say it's got two P's for two protons. And what else is released? Yeah, photon. Energy, photon. So I'm going to write the word photon. I'm going to put that in my little flash of kind of light. So we're going to have a photon and heat energy. Now, when you become a nuclear physicist or an astrophysicist, you will also find other things will be released, like little neutrinos, right? We are not talking about that right now. We are just keeping it simple, going through the basics. Fabulous. This works really well only until iron. Only works up to elements smaller than iron, or to iron? Iron is Fe. That's the chemical equation. It's Latin for ferrous. A lot of my students say, why don't they just call it iron? Well, because the scientific world is not, ruled by only Americans. Science is a language of Latin. So you'll see a lot of Latin, you'll see a lot of Italian, French, not only English. And we'll talk about what happens when iron starts to be fused in stars. When iron starts to be fused in stars, it's the death of the star and the star explodes. It's like, oh, whoops, sorry, nova, gone, supernova, and everything that was created in that star is then blown out into the universe, which is why we have iron on our planet. The basis of why we're here shows that there was a star that died. Okay, many stars died in order to give you the life you have today. It's like a true, Star Wars story. Let's go ahead and look at what stars produce. Stars produce lots of energy, baby. They make heat. They produce visible and non-visible light. So I'm just going to say visible light because we already said energy. And they produce new elements. So I guess I should put like a dot on each one of those. Dot, 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 dot. Now, here's where the color pictures come in on your piece of paper. The first one is the continuous spectrum. And what did we say the spectrum was? What's a spectrum? Spectrum is another word for range. This is the range of colors in the visible light spectrum. Okay, range of colors. Below, it says emission spectrum. What does it mean to emit something? Lizzie? To release something. Okay, what does absorption mean? That's the one on below. What does to absorb something? Adam? Yeah, hold it inside of you. Like if water absorbs into a sponge, it soaks up that water and it holds onto it. This is what elements do. Elements need energy, baby, because they've got electrons that are moving all over. Those electrons need energy to move. Where do they get that energy from? It's like they steal it from the light. So I can't bring the star to you to study, but I can bring the star's light down to you to study. If you see something like this absorption spectrum down here, this is the fingerprint of an element. I want you to write the word fingerprint. It's the missing lines, the missing wavelengths of light. Jacob, do you see the little black lines in here?
Yeah.
That's because there's an element inside that star that is holding on to that light and not letting it come down to us. We are able to see missing parts of the visible light spectrum. And if you're trained, you know what element that would be. And you can study the star's light and figure out what the chemical composition of the star is, what elements are being held in that star, just by the light that is missing after it comes down to us from Earth. We're going to be doing an activity on Monday about this, but we're getting to start today with some notes. So we're going to start over here by saying different elements absorb different. I'm going to say wavelengths, but I'm not going to write wavelengths. I'm just going to use our symbol for wavelengths. Wavelengths of light? By identifying the missing parts. The missing parts of the visible light spectrum we can tell which elements are in the star. Just by seeing at what light is missing. I'm going to bring you through an investigation on Monday. And do you see all of these lines? These lines represent the fingerprint for hydrogen, helium, sodium, magnesium, calcium, and iron. I'm going to give you different stars to look at, and you're going to try to see if you can identify what elements are hidden in what stars. Okay, we're going to be doing that on Monday. So now we have enough information to answer the questions on the side and do a summary on the bottom. You are going to do that after this class. My recommendation is to do it tonight so that you go over the information and it's fresh in your mind. All right, let's turn to the back side of the page, please. Caden, could you tell me how much time I have left? 20 minutes? 15 minutes? You're not dumb. No, you're not. All right. So our essential question on this one, I'm going to go with 15 then. So our essential question on this side is, how are stars different from one another? How are stars different from one another? Because not all stars are the same. Not every star is just like our sun. All right, we are going to classify stars using something called the HR diagram. The H stands for a man with the last name of Hertzsprung. And then we say dash, and the other man's name is Russell. It's the HR diagram, or the Hertzsprung-Russell diagram. This diagram is not a map of the universe. It is a classification system. Okay, so what they do is they look at a star and they say, how hot is that star? How bright is the star? What color is the star? Oh, okay, then that star goes right here. So it's a classification system, and I'm going to explain it to you now. Let's look at temperature first. Notice on this side, we have our cooler stars. Please write what I'm writing. On the other side, these are our hotter stars. It is based on a temperature called Kelvin, Kelvin. Sir Kelvin created this based off of absolute zero. You're not familiar with Kelvin, but you are familiar with Fahrenheit. So what I'm going to do is I'm going to put at the top here 70 degrees Fahrenheit. 70 degrees Fahrenheit is the same as 21 degrees Celsius. 21 degrees Celsius is the same as 294 degrees Kelvin. So 25,000 degrees Kelvin is super stupid hot. I mean, even 3,000 degrees Kelvin is really hot, right? They're hot. You can't go up and give a star a hug. So it's not a cool star, but it's a cooler star. Now, on the electromagnetic spectrum, if we look down here at the bottom, do you see where it says spectral class? Spectral means star. Please write the word star underneath that. Next Wednesday, you are going to be at home watching a video, and it is a Cosmos episode, and you will be introduced to a woman called Annie Jump Cannon. She created this classification system on the bottom, and it classified stars by color. So does anybody understand, based on the visible light spectrum, what is our cooler stars? What would be 3,000 degrees? What color? Remember, we've got red all the way to purple. What do you think? Purple is not cooler because that's high energy. So long wavelengths, cooler. So in this case, our cooler stars are going to be our red stars. Those are going to be down here. Our blue stars are going to be our warmer stars. Those are going to be over in this area. And then it kind of goes to like white hot over here. Our sun is what's called a G star, and it is a yellow star. So this is based on the visible light spectrum. Cooler stars are red. Now, Hayden made the same mistake everybody else makes. They look at blue and they think it's like cold and ice and frozen. It's not like that. Cooler means longer wavelengths, less energy. Let's look at luminosity, please, over on the side of the scale. Luminosity is based on luminosity of 1. That's our sun. Our sun is where we started this rating. Anything higher than 1 are going to be our bright stars. So if you could write that. What's up, Lizzie? It's just, I don't know what she has the G stand for. That's a really good question. I don't know what it stands for. Anything below 1 is going to be our dim stars or dimmer or faint stars. Our sun is a G yellow star with a luminosity of 1. So if we connect those two things, we can see that our star, our sun, would be classified somewhere in this area. This would be where our sun is. Now, each one of those teeny little dots is a star. And again, it's a classification system. It is not a map of the universe. So if you look at our sun and you say, yep, it's yellow and it is a luminosity of 1, it goes here. It's not going to go there forever. When it ages, it's going to go ahead and transition into a red giant star, and we're going to have to classify it here. Caitlin.
The shape of the diagram that's shown on the diagram, it looks like the symbol that we just played in.
It kind of does, doesn't it? That's a good comparison. This symbol that she's talking about that runs all the way through, this is what's called the main sequence. If we classify our stars, most of the stars in our known universe right now fit on the main sequence in classification. The dwarf stars typically look like they all get classified here. Our giant stars classify here, and our supergiant stars classify here. And again, because our sun is here now in its age, sun is like in middle age. You gotta write this stuff down. Our sun is going to transition and eventually not going to be able to be classified here anymore. It'd be like if you looked at Mrs. McGrain when she was 18 years old and you tried to classify me by like my weight, my hair, whatever. You'd put me in a certain area, but now I'm no longer 18. So I am not the same. I don't have the same characteristics. You'd have to say, well, let's look at her at this age. Well, she's no longer here. Now we have to put her here, right? Just like stars, when they get older, they swell up. Mrs. McGrain's swelling up a little the older I get to. So we change stars' classification depending on their age. All right. Let's go ahead and move down, and I'll explain what some of these symbols or some of these titles are, like luminosity. Luminosity is all about how much energy a star gives off. So luminosity, how much energy a star emits. I'll say emits. Okay, this is dependent on the size of the star and the temperature of the star. I will give you an example. If you look at a supergiant star, it is 3,000 degrees. It's cooler than a dwarf, right? But look how much brighter it is. It's putting off so much more energy, even though it's a cooler star. And that's because it's just got so much more surface area. And so it's got so much more surface area that it's putting out much more energy than a smaller star. All right, let's look at brightness. Brightness changes with distance. It'd be like if I took a flashlight and shined it directly into Claire's eyes, she'd be like, that's really bright. Get away. But if I went a mile down the road and shone that same flashlight, now it wouldn't be as bright. So this is what absolute magnitude is all about. We're going to write absolute magnitude. To figure out what a star's absolute magnitude was, what they did was they said, we're going to imagine that all of these stars are an equal distance of 32.6 light years away, and then we're going to judge how bright they are. So absolute magnitude is brightness at a distance of 32.6 light years. If we could imagine all of the stars lined up at that same distance, this is how they're going to rate on the scale of absolute magnitude. Landon, how close am I on time? 3 minutes. Size. I already showed you the size on the diagram. I'll tell you our sun is a medium dwarf star. It is on the main sequence. That is where it'll spend most of its life. But you can have giant stars, you can have supergiant stars. Mass determines the life of the star. Smaller stars is going to be longer life. Because smaller stars burn through their energy at a slower, they just don't need as much fuel to survive. Massive stars burn through their energy supplies very quickly, and they die very fast. Chemical composition. I'm going to look at the main sequence stars. And I should say for chemical composition, let's put a parenthesis here. This is what elements are in the star. Main sequence stars. Most of the stars in the universe classify on the main sequence. Most stars spend the longest part of their life there. Our sun is right now in middle age, so it's there as we classify it there. Longest part of life. And Our star and all the stars on the main sequence are currently fusing hydrogen into helium. Our sun is a hydrogen star. It is fusing its hydrogen gas into helium. Woo! And now you have information to go ahead and answer that part. Please make sure that you do that. If you are interested in the retake, please